So the first example we want to talk about is actually a proportionality problem. And we are going to start out with the growth rate is directly proportional to the amount. So if we let y equals f of x be the amount or population or whatever you want to call it, our differential equation is going to have the form, so our growth rate would be dy dt, because that's our slope, or dy dx in this case. This is our slope, or our rate of change, is equal to, or is proportional to, so our proportionality constant times the amount. So then dy dx, or the derivative of y with respect to x, would be equal to k times y. This says that the growth rate is proportional to the output of the function at every point, right? So it says the growth rate is some constant multiple of the y value for all of these things. So often in problems of this type, the independent variable will be time. And we'll denote that with t. So if P is the population at time t, then we get this version of the differential equation. dp dt is equal to k times p. So this is called a differential equation because the equation involves an unknown function p of t and its derivative dp dt. A solution to a differential equation is a function that makes the equation true for all t. So we're generalizing the idea of an equation. So in algebra, a solution to an equation was a value of a variable that when we plugged that number into the equation, we got a true statement. A solution to a differential equation is a function that when we plug it and its derivatives into the differential equation, we end up with a true statement. So let's go ahead and look at an example. So we wish to show that y equals sine 3x is a solution to the differential equation y double prime plus 9 times y is equal to 0. So this differential equation says that the second derivative of the function plus 9 times the original function should equal to what? 0. Okay, so we need to find two derivatives of y. Well, when we look at y, we notice that y is a composition. So f of u is sine u, and u is equal to 3x. So then y prime is df du times du dx. So that's going to be the derivative sign is cosine u times du dx is 3. So we back substitute and we get y prime is going to be 3 times the cosine of 3x. Well, we need to rinse and repeat. So once again, this is another composition. So f of u this time is going to be cosine. And u once again is 3x. So then y double prime is going to be df du times du dx. The derivative of cosine is going to be negative sine. So we get negative sine u times du dx, which is 3. So then we get our derivative and back substitute. So y double prime is 3 times 3 times a negative gives us negative 9 sine u, but u is 3x once again. So the second derivative of sine 3x is going to be negative 9 sine 3x, right? So now let's check that. If we put this into our equation, y double prime, we get negative 9 sine 3x plus 9 times, we need to plug in the original. Well, what was our original equation y? Sine 3x, right? And we want to know, does that equal to 0? And indeed it does. Because we get negative 9 sine 3x plus 9 times the sine of 3x equals 0. So it checks. So that was indeed a solution to that differential equation. So a solution is sine 3x. All right. All right. So let's determine if this is a solution. So when we take our derivative, the derivative of e to the negative 3x is going to be negative 3e to the negative 3x. And we get that by using the chain rule. And our second derivative, y double prime, is going to be 9 times e to the negative 3x, and that's the chain rule again, right? So something we may have noticed as we've been moving forward, when we have composition with a linear function, what does our derivative always turn out to be? So in the previous example, we had sine 3x. What was its derivative? Well, what's the derivative of sine? Cosine. But then what did we have to multiply by? 3, right? The 3 was the slope of the linear function on the inside. When we have a linear function, that's always going to be true. So if you have composition with a linear function, it's just going to be a regular derivative times the slope of whatever the inside function is. Because when we write out the composition, what's the derivative of 3x? Well, since it's linear, the derivative is the slope. And what's the slope of 3x? 3. Fast forward to your problem. What's our inner function? Negative 3x. So what's the slope of negative 3x? Negative 3. So when we take the derivative, y prime is negative 3 times e to the negative 3x. If we take the derivative again, our constant stays down in front. What's negative 3 times negative 3? 9 e to the negative 3x, right? You can use the chain rule every time, but with linear functions, you're always just going to be multiplying by that slope. It is something that will make our lives a little bit easier. So then if we plug this into our equation, we then have 9e to the negative 3x, take away 9 times our original function, e to the negative 3x. And we want to know, does that equal to 0? And the answer is yes. So yes, it is a solution. All right. So we can check that something is a solution to a differential equation by just plugging it in. So we are not going to spend time in this class trying to solve differential equations. That is a topic for another class. But we will attempt to guess the solution to a certain differential equation. So this is the one we were talking about at the very, very beginning. So what does this differential equation say then? It says that the derivative is equal to a constant times the original function. Well, what function do we know is equal to its own derivative? Hint, you just did it in the last U try. What's the derivative of e to the x? E to the x. So what's the derivative of e to the kx? E to the kx times k, right? Because you got to do the chain rule with the derivative of the inside. So we're going to guess our solution, and we will guess that the solution is P equals, A is going to be some constant, e to the kt. So then if we take the derivative, dp dt, the constant comes out of the derivative, and what's the derivative of e to the kt? Well, it's k e to the kt. So let's check if this is a solution. So that gives us a times k e to the kt. That's dp dt. We want to know, question mark, does that equal k times p, which is a e to the kt? And yes, it does, right? So it turns out that p equals a e to the kt is a solution the equation. So, in general, the solution to y prime equals ky for the general proportionality problem is y equals y of 0 e to the kt, where y of 0 is the starting amount. That is the amount at time t equals 0. Y of 0 is called the initial condition. So basically, the initial condition just tells you how many things you had to have at the start, right? Because this solution works for any arbitrary constant. That arbitrary constant is determined by the initial condition of the system. So if you start with a population of 100, that would be your initial condition. If you start with a population of 10,000, that would be your initial condition. All right, so before we move on to example 2, there are a few things that I do want to mention. So a lot of these problems we've seen in a pre-calculus class, and we've potentially seen these problems in either a chemistry or a physics class, or maybe even a biology class. So math uses a different convention for all of these. So for those of you that took pre-calculus here, our pre-calculus class used the convention from chemistry, math, and biology, which is they introduce minus signs into the solutions of all of these things because physical sciences generally want their rates to be positive numbers. So they require their proportionality constants to be positive. Mathematicians are a little more abstract. We don't care. So we don't put minus signs in our formulas. The result of this is we have one formula for all of these problems. Whereas in previous classes or in, say, chemistry or physics, if you have a growth problem, it's going to be of the form we're going to talk about in a second. If you have a decay problem, it's going to be the same formula, but they put a minus sign in front of the growth constant. So it'll be a negative k versus a positive k. In our math classes, we don't distinguish because when we solve the problem, it will work out the sign of k automatically, as we will see. If k is positive, it means growth is happening. If you get a negative answer for k, it means it's decreasing or it's a decay problem. Whereas in the physical sciences, they presuppose that it's either growing or decaying and select their model, whereas we solve the general model and then decide afterwards, is it growth or decay? So we'll see that in action here. So the only reason I mention this is some of you will have seen formulas where there's these minus signs, and we had to remember which time do we pick which formula. In calculus, there's one formula, and the constant will sort itself out when we use the initial conditions. So different perspective, but we get the same solution in the end. I just want to forewarn you before you get confused and are like, hey, we used a different formula before. We're just actually using a more general version of those specific formulas. All right, so in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. The experiment starts with 100 flies, and after 2 days, there are 300 flies. How many flies will there be after 10 days? Okay, so we are going to start with our solution to our differential equation, which is y equals y of 0 times e to the kt. So going back, what was y of 0 again? Y of 0 is the starting amount. So in this problem, how many flies did we have at the beginning of this experiment? 100. So we started with 100 flies. So y of 0 is going to be 100. So let's put that into our equation. So we get y equals 100 e to the kt. Step 2 is we need to find an ordered pair so a t and a y that pair up and use it to solve for k. So we go shopping and we're told that after 2 days there are 300 flies. So we get the ordered pair, our t and our y, are after 2 days we have 300 flies. So our y is 300 and our t is 2. So we're going to put these values into our equation for t and y. So our y value is 300, so we get the equation 300 is equal to our 100 times e to the k, which we don't know, times our time, which is 2. And we need to solve this equation for k. So this is an exponential equation, so we need to get the exponential by itself. So we divide both sides of the equation by 100, and that gives us 3 equals e to the 2k. The inverse of an exponential base e is the natural logarithm. So we take the natural logarithm of both sides, and when we do so, the e and the natural log reduce out. And we get the natural logarithm of 3 is equal to 2k. We divide by 2, and this gives us k is equal to the natural logarithm of 3 divided by 2. All right, step 3. Now that we have our growth rate, we are going to put k back into the equation from step 1. So that gives us y equals 100, because that was our initial population, e to the k, and our k is the natural logarithm of 3 over 2 times t. So this is a perfectly good answer, but we can do some algebra. We can simplify. If we wish. So it's worth noting. The simplification will be nice, though. So we have the natural log of 3 over 2 times t is the same as t times the natural logarithm of 3 over 2, which we can write as t over 2 times the natural log of 3. And then by our power rule, for logarithms, we finally get that that is the same as the natural logarithm of 3 raised to the t divided by 2, right? If I put that back into my original equation, I get y equals 100e to the natural logarithm of 3 raised to the t over 2. But the e and the ln are inverses. So they reduce out, and this simplifies down to 100 times 3 to the t divided by 2. In fact, this formula might look familiar. We used or guessed some formulas that looked like this back in Chapter 1, right? In Chapter 1, Section 6. Those were special cases when we had doubling time of this more general problem, but we can always reduce them to a nice exponential like this. The thing is, when we go to get the final answer, whether you use this or this, you're punching it into your calculator doesn't care, right? It doesn't care if you were simplified or not when you put in the t. It will give you the same answer in the end, because it just crunches it all into decimals anyway. So then finally, step 4 is we're going to answer the question. So our question was, how many flies will there be after 10 days? So we want y, so our question is, we want y when t equals 10. So the way step 4 is always going to work is they're going to give you half of an ordered pair and ask you to find the other one. In this case, they gave us the input t and asked for the output y. They can just as easily give you the output y and ask for a t. So they could have said something like, well, when will the population be 5,000, right? So they give you a population and then say, well, how long is it going to take for it to grow to that amount? All right, so this one we just put in 10. So y of 10 is going to be 100 times 3 to the 10 over 2. So 100 times 3 to the 5th power. And from here we just grab our calculator. And 100 times 3 raised to the 5th power gives us 24,300. All right. So the next problem we want to talk about deals with chemistry. So specifically, we want to talk about radioactive half-lives. So the half-life of a radioactive substance is the amount of time it takes for 50% of the substance to decay into different elements. So we're not going to get into the details of alpha decay and beta decay, but essentially a radioactive substance emits subatomic particles and loses atomic mass. When it does so, it changes the chemical composition of the radioactive substance. The resulting substance may or may not be radioactive and may continue a radioactive decay chain. But for us, the only thing we really need to know is that the half-life is the amount of time it would take for 50% of that substance to transmute into something else. So using this, we can actually use our proportionality problem. So if we start with y equals y naught e to the kt, so notice I mentioned this at the beginning. If you were in a chemistry class, they would put a minus sign in front of that k because they're assuming decay. We're not going to do that in our class. We will solve for the minus sign as this happens. So that's why I'm saying in our math classes, the sign will actually tell us whether it's growing or decaying. So we get this, and we're going to let h be the half-life. Then we know the following. Y of h would have to equal to what? Well, the half-life says we have 50% of what we started with. So then y of h would have to be 1/2 times the starting amount, right? If we started with y naught, we don't know what that is, but we know after one half-life, by definition, we would have 50% or half of it. So y of h has to be 1/2 y naught. This gives us the ordered pair h, comma, 1/2 times y of 0. So we can now use this to solve for k. So we put this in, we have 1/2 y of 0 is equal to y of 0 times e to the k times h. So we isolate our exponential by dividing both sides of the equation by y naught. So something very interesting happens. The starting amount reduces out of our equation. So our mathematical model tells us something interesting about this. It says that our decay rate, k, does not depend on how much of the substance there is. So what does that mean in terms of reality? That means the time it takes for 1 kilogram of plutonium to decay to 50% of its original amount is the same amount of time it would take 1 million kilograms of plutonium, right? The initial amount doesn't matter. It's only proportional to time, is what this is really telling us, right? So the growth rate does not depend on the amount of the substance, which is interesting. Okay, so now we finish solving this equation by taking the natural log, and we get the natural logarithm of 1/2 is equal to k times h. We divide by h, we divide by h, and we have h is equal to the natural logarithm of 1/2 divided by h. It's traditional to use the quotient rule or quotient property of logarithms on this. So that's the same as the natural logarithm of 1 minus the natural logarithm of 2 all over h. And what's the natural logarithm of 1 equal to? Well, e raised to what power gives you 1? 0, right? So the natural logarithm of 1 is 0. So finally, after all of this, I wrote h there. That's a typo. We divided by h, so that's k. Everybody needs to make sure they didn't write down. I put an h there. I divided both sides of the equation by h. The h is reduced out and left a k behind. Otherwise, you're going to get really confused. So this absolutely has to be a k. So then we get k is equal to the negative natural logarithm of 2 divided by h. So this tells us for radioactive decay problems, the growth rate, or in this case the decay rate, is the natural logarithm of 2 divided by the half-life, but it's negative. That's how we know it's a decay rate. So if we were to plug that back into our original formula, that's where the minus sign comes in. So in chemistry, they put it there, and when they solve for this rate, it's going to be positive, and when they substitute it back in, there's already a minus sign there. In math class, when we do it, we solve and get the minus sign. Either way, we get the same thing. So just two different ways to get the same solution. So this tells us then if a substance has half-life h, its decay rate is given by k equals the negative natural logarithm of 2 over h. So basically what this does for us is in radioactive decay problems, we get to skip step 2, right? Because what was step 2? Solve for k. Well, this just gives us a formula that allows us to know what k is immediately. All right. So I forgot to let you guys do your U-turn. All right. So we want to find the decay constant k. Well, we know from the work we did earlier that k is the natural logarithm of 2 divided by h, where h is the half-life. So the half-life of cesium-137 is 30 years, so it's going to be the ln of 2 divided by 30. And we want to know, well, how long until there's only going to be 1% left. So let's write out our equation. So we're going to have y equals y of 0 times e to the k, which is the negative natural logarithm of 2 over 30, times t. So we want to know, well, how long until there's only 1% left? Well, we have y naught in our equation, and we weren't actually given an amount in this problem. We were only given percents. Well, what is it that y naught stands for again? The amount at the beginning, right? So if we weren't told how much we started with, we're going to assume that y naught is 100% because we weren't told, right? And what is 100% as a decimal? Because we can't use percents, right? So we turn it into a percent, we turn our percent into a decimal and we get 1. Well, we want t when y equals 1%, but what's 1% as a decimal? 0.01. So we need to solve 0.01 equals 1 times e to the negative natural logarithm of 2 over 30 times t. So once again, it's worth noting, if we simplify this using some of our log properties, this is the same as e to the negative t over 30 times ln 2, which is e to the ln 2 raised to the negative t over 30. Something very interesting happens. Once again, those reduce out. And what are we left with? 2 raised to the negative t over 30, right? It's the same thing we did in the previous problem when I got the 3. We can always do that with our k's because our k's will always involve a logarithm. So essentially we can move some constants around and use our power property of logarithms to reduce the e and the log out. So now the equation we need to solve is 0.01 equals 2 raised to the t over negative t over 30. So then we take our logarithm of both sides. So the natural logarithm of 0.0, sorry, let's not do the natural logarithm. We'll do the logarithm base 2. So the logarithm base 2 of 0.01 is equal to the logarithm base 2 of 2 to the negative t over 30. And when we choose the logarithm base 2, those guys reduce out. And we're left with the logarithm base 2 of 0.01 equals negative t over 30. So we multiply by negative 30, multiply by negative 30, and we get t. So then we just punch this into our calculator. And I said it kind of fast last time. If we don't remember, where is the logarithm with an alternate base? So we're going to have negative 30, and then we press alpha and window. Choice number 5 is our logarithm with a different base. So we go down to choice number 5. Logarithm base 2 of, not 2.01, log base 2 of 0.01. And we press enter, and we get 199.31. So we get t is approximately 199. So it would take about 199 years for 99% of the cesium-137 to decay. So the last one is, what percent is left after 120 days? Okay, we have to be careful here, because in the original problem and in math classes, we play loose and easy with our units all the time. What are our units of K? What was our original time given in? And what are we asked here? So we can't just put in 120 or we're going to get a lie, right? Because if we put 120 in, it's going to tell us how much is left after 120 years, not how much is left after 120 days. So we must be careful and convert days to years. So if we have 120 days, we'll use the fact that there are 365 days in 1 year. So 1 year, not plural, 1 year is 365 days. So we can do that on our calculator. 120 divided by 365. That gives us that 120 days is 0.32876 blah, blah, blah years, which seems reasonable. 120 days is about a third of a year, right? So then we need to put that in to our equation. So our equation is y equals 1, because that's our 100%, and after we simplified, we didn't have the e anymore. We had 2 raised to the negative t over 30. So now we just need to put this value in for t. So we do that on our calculator. So 2 raised to the negative. And if we want the answer from the previous line, we get that by pressing second and our negative key down here at the bottom. So this guy. And then we divide it by 30. And we get 99.24. So that tells us that there would be about 99%. And depending on what they ask you to round to, you might need to say 99.2% or whatever is appropriate. All right. The last model we want to talk about is called Newton's law of cooling. So Newton's law of cooling is a variation on this law. So Newton's law of cooling formally states the following. The rate of change of temperature of an object is proportional to the difference between the object's temperature and the object's surroundings. All right, so it says the rate of change of the temperature of an object is proportional to the difference between the object's temperature and the object's surroundings temperature. So what does that mean? That means that the derivative, the rate of change of the temperature of an object, so capital T. Oh, before I do that, I should define that. So let capital T be the temperature of the object. And little t is time. So then we would get the following. The time rate of change of temperature, so d capital T, d little t, is directly proportional to, so k, and then it says the difference between the object's temperature, so T, and its surroundings. So then we'll call that T sub S. So this is a little bit different than the models we saw before, but that should also make sense. If I take a pie out of the oven and set it on the counter in my kitchen, is that pie ever going to cool down cooler than the temperature in my kitchen? No, right? So what that's saying is that the rate of change of the temperature of the object is proportional to the difference between the object's temperature and the room temperature. So the bigger the difference, the faster it's going to cool off, right? When you first pull something out of the oven, it's going to cool off faster But the closer something gets to room temperature, the slower it is going to cool down. That's what this differential equation is telling us, is that the rate of change of temperature is proportional to the difference of the object's temperature and the room temperature. So this one doesn't quite fit the form that we did at the very beginning, right? We guessed a solution to this differential equation, dp dt equals kp. Well, we have dt dt equals k times t minus t sub s. So it's got an extra little bit to it. It's got the same part, but a little bit more, right? Well, it turns out that we can, quote unquote, fix this equation. So let's let y of t equal t minus t sub s. And if we solve this equation for t, we then have t is equal to y of t plus t sub s. So I just add t sub s to both sides. I can also take the derivative of both sides of this equation. So if I do that, I get y prime of t is equal to t prime minus, and we're going to assume that the room's temperature is constant. You can model these when it's not, but it makes the problem harder. Take differential equations. They'll solve that problem. For us, we're going to assume that room temperature is constant. If room temperature is constant, what's the derivative of a constant? 0. So then y prime of t would equal t prime, or dt dt, right? Because that's what t prime means. Okay. So now, if we substitute all of this into the original equation, we're going to end up with y prime is equal to k times, and we have that t minus t sub s, well, what is that the same as? Well, that's going to be just y, right? This is the original problem that we started with, right? Y prime is equal to ky. So by making the appropriate assumption that room temperature is constant, by making a substitution, we transformed Newton's law of cooling into this differential equation. Okay, we know the solution. What's the solution to this differential equation? So the solution is we have that y of t is equal to y of 0 times e to the kt, right? That's the solution that we've been using. But now we need to get back to the original problem that we started with. Because we didn't start with y, we started with t's, right? So now we need to do some substitutions. So the first thing we're going to note is that y of t was equal to this. So when t equals 0, we have y of 0 is equal to t of 0 minus t sub s. So that's going to be this right here. So if we substitute that back in, and we resubstitute back in our y value from here, right? We finally end up with t minus t sub s is equal to t of 0 minus t sub s times e to the kt. So then if we solve that for t by doing this, we get that t is equal to t sub s plus t of 0 minus t sub s times e to the kt. So this might look familiar. From pre-calculus, they just gave you that equation, right? And said, use this to solve the problems. They didn't bother to tell you that it was this differential equation and how we're going to solve these problems. So I did this part just to relate it back to what you've seen in Math 187. When they give you Newton's law of cooling, they give it to you in that form and just say, plug some numbers in and ta-da! Well, we're going to use the other version in our next example. All right. So let's solve this in general. So example 4. The police discover the body of a murder victim. Critical to solving the crime is determining when the murder was committed. The coroner arrives at the murder scene at 12 p.m. She immediately takes the temperature of the body and finds it to be 94.6 degrees. She then takes the temperature 1 hour later and finds it to be 93.4 degrees. The temperature of the room is 70 degrees. When was the murder committed? All right, so we start with our model, which is y equals y of 0 e to the kt. We know that y of t was equal to, and I'm going to write it as a function of t to make it clear, minus t sub s. Well, we know what t sub s is. That's the temperature of the surroundings. And our room temperature was 70 degrees, right? So we get that y of t is equal to t of t minus 70 degrees. All right. So we then need to find out, well, what is y of 0? Well, y of 0 is going to be the same as t of 0, take away the 70 that we just found. Well, t of 0 is our starting temperature. What was the temperature of the body when the CSI showed up? So when she showed up at noon, she immediately took the temperature of the body, and it was 94.6 degrees. So then we get 94.6 take away 70. So that gives us that y of 0 is then equal to 24.6, right? Okay, so now we have y of 0, and we can put that back into our equation. So we've now finished step 1. Y is 24.6 e to the kt. So our normal step 2 is we need to find a time and a temperature that go together. So a time and a temperature that pair up. Well, our time and our temperature that pair up is, we know after 1 hour, the new temperature of the body was 93.4. So 1 and 93.4. But the problem is, in our model, we have y's, we don't have t's, right? So we must convert from t's to y's. Well, luckily, we have an equation that is going to help us do that, right? So we know that when t is 1, when little t is 1, big T is 93.4. So y of 1 is going to be equal to t of 1, take away 70. So t of 1 is 93.4, take away the 70, which is going to give us 23.4. So this gives us the new ordered pair when t is 1. So the new ordered pair t comma y is when t is 1, our y value is 23.4, right? We can use this ordered pair to solve for k. So then we're going to use this to solve for k. So we get 23.4 is equal to 24.6 times e to the k times 1. So 23.4 is equal to 24.6 e to the k. We divide by 24.6, and we divide by 24.6. So we have 23.4 over 24.6 is equal to e to the k. So we take the natural logarithm of both sides to undo the e. They reduce out. And that gives us that k is equal to the natural logarithm of 23.4 over 24.6. So then step 3 is we substitute our k back into our original equation. So that gives us y equals 24.6 e to the k. I'm going to do t times the ln of 23.4 over 24.6, which is 24.6. Moving our t up into the exponent, e to the ln of 23.4 over 24.6 raised to the t. And then the e and the ln reduce out like they have in all of our other models. And we finally get y equals 24.6 times 23.4 over 24.6 raised to the t. All right, so that's our model. And finally, step 4 says, when was the murder committed? And then it gives us the hint, 98.6. So we want big T when, or we want little t, sorry, when big T equals 98.6. But we have a bit of a problem. The equation we have doesn't have big T. What does it have in it? y. So once again, we have to use this. So we know y of t is equal to t of t minus 70. So y of t is going to be, we want to find this when it's 98.6 take away 70, so 28.6. So we want t when y equals 28.6. All right, I'm going to have to stop here because it is now 10 o'clock, but I'm 100% positive you can plug that in for y and solve for t, right? So at this point, I know you can finish up from there, so we'll call it a day. So solving for t, we put 28.6 in for y equals 24.6 times 23.4 over 24.6 to the t. We isolate our exponential by dividing by 24.6 and dividing by 24.6. And we get 28.6 over 24.6 is equal to 23.4 over 24.6 raised to the t. And then if we just take the natural logarithm of both sides, we can bring the t down in front of our logarithm and solve for it. So that gives us the natural logarithm of 28.6 over 24.6 equals t times the natural logarithm of 23.4 over 24.6. Divide by our natural logarithm on both sides of 23.4 over 24.6. And finally, that gives us our value of t. So we grab our graphing device. And we put in our fraction, and then logarithm, another fraction, 28.6 over 24.6 over logarithm, another fraction, 23.4 over 24.6. Enter, and we get the following value. So first, it might bother you that we get a time value that is negative. Often in problems we say that time can't be negative, but actually in this problem it's a good thing. So we get that t is about -3, which means the murder happened three hours before. p.m. So the murder happened at about 9